Hello and welcome to our today's webinar about the application of cloud-based CFD for the optimization and development of industrial blowers. My name is Milad and it's a big pleasure for me to be today's host. I'm the product marketing manager here at SimScale. As part of my role, I'm organizing and conducting several workshops and webinars on a regular basis about a wide range of topic, and here the aim is to introduce new users to the world of simulation. Before joining SimScale, I've gained a lot of different experience in 10 years in different industries about the application of simulation, including motorsports, automotive, and aerospace industry. And before we start to dive in our today's topic, I would like to quickly discuss today's agenda with you. As you know, the idea of this webinar is that the participants get introduced to the fundamentals of simulation and how it can help in the design of industrial blowers. Therefore, we will talk a little bit about the general benefits of simulation at the beginning, and I will also introduce you to SimScale, our free and cloud-based simulation platform. And after that, we will start to talk about, let's say, our today's application. So we will talk about industrial blowers and how they can be optimized using CFD. Therefore, we have prepared what we call a live demo. This is a real-world simulation project which shows you clearly how CFD can be applied to industrial blowers and how the results can be used to optimize the design. We will discuss the results together, and after this we also have time for a Q&A. So in the case you've got questions, we have a window called questions inside the GoToWebinar application, which we're using to provide you with the live stream of this webinar. And if you have a question, just write your question inside this box and I will try to answer it on the fly or latest during the Q&A. All right, let's start to talk a little bit about the benefits of simulation. And since we have a lot of participants and everybody has a different background, let's try to summarize some of the real fundamentals you need to know to understand what we're going to do in the next 30 minutes. So first of all, simulation, also called CAE, is a technique which is now used for more than 40 years to virtually optimize the design of products and machines. And the idea of simulation is that we can replace physical testing by virtual experiments, and a very big part of simulation is called CFD, which stands for computational fluid dynamics, and CFD describes all simulation techniques we can use to predict the behavior of a fluid flow substance. And the great advantage about simulation in general, CFD, is that it actually allows us to test the design correctness and the efficiency of our design without having the need to manufacture a physical prototype first. If we think, for example, about, and this is, by the way, I think the best example, about aircraft designers, aircraft aerodynamists. They cannot build an entire one-to-one model of the airplane every time they want to test something. And in addition, there is even not one wind tunnel in the world which is large enough to put a real aircraft inside. So what they do instead of is using fluid flow simulation, which means they don't need to have a test rig, they don't need to have a wind tunnel, they don't need to manufacture a wind tunnel model, which can take a lot of time and be very expensive. And it's not only about, that we can replace physical testing with simulation, but it also has some advantages, some unique advantages, which I would like to discuss with you quickly. So first of all, simulation helps you to reduce time. It's not only, let's say, cheaper than physical testing, but it's also much quicker. Usually, for example, to run a CFD simulation of a full aircraft, it will take you maybe around 3 to 4 days to set up everything, run the simulation, and get the results. If you want to do a wind tunnel test, you will need at least maybe 1 week just to prepare the wind tunnel and the measurements. So obviously, whenever it comes to design things fast and efficient, simulation can help a lot. But it's not only about saving money and costs, it's also that CFD, or simulation in general, provides us with a totally different approach to data. If I do, for example, a physical test, a wind tunnel test, I need to measure all the quantities I'm interested in during the run. So if I want to know about the forces, I need to install wind tunnel scale. If I want to measure the pressure at points, I need to install pressure probes. And whatever I don't measure during the run is lost. And with simulation, it's completely the other way. Actually, I can run the simulation and access all the field values during the post-processing. So simulation gives us a completely different access to the physics of our problem, because it allows us not only to understand what is happening, but why it is happening. And from what I've told you so far, you must think simulation, or in particular CFD, is such a great tool. And you maybe also think it's an industrial standard, but you will wonder, because actually it's not. Only 5 out of 100 engineers have access to simulation technology. And back then, 6 years ago, when SimScale was founded, the vision of the founder team was to make simulation accessible to every engineer in the world and to somehow democratize simulation. And there are actually 3 main reasons, or 3 barriers, which why simulation, or traditional on-premise simulation tools, were only adapted by a minority of users. First of all, traditional simulation solutions comes with a high upfront investment. You need to buy the software licenses, which can easily cost you as much as a new car. You need to buy dedicated hardware, and there you need special hardware for computing, with a lot of memory and a lot of computing power, CPU power. You need special machines for visualization, where you need high graphic performance. And this was a big problem, especially for small companies in the past, because if you just want to use simulation for, let's say, a single project, it doesn't make sense to pay a simulation license for 1 year and to buy the infrastructure, which can be used for up 3 to 4 years. Besides this, it's another barrier, which we call the access barrier. And let's imagine you got this hardware and the software for free. You still need someone who is able to prepare and maintain the infrastructure you need to perform the simulations. And usually this means you need a cluster where you can, different computers can parallelly compute your solution. You need, as I mentioned, dedicated workstations with high performance video cards to visualize the results. And since simulation results are usually very, very large, for example, the aerodynamic simulation of an aircraft can easily take up to hundreds of gigabytes of data. And you also need like a solution for that. And latest at that point, usually small companies say, okay, it sounds great, but we can't use it because it's too much of overhead for us. And even if we say we can solve barrier 1 and 2, there's a third barrier, which is, from my point of view, maybe even the most important barrier, which we call the knowledge barrier, know-how barrier. Because even if you have access to the tools and the infrastructure, most of the traditional simulation tools are designed, let's say, for simulation experts, for numerical experts, and not for design engineers or mechanical engineers who are actually designing the product and who only want to apply it as a tool. And yes, that was the reason why SimScale was founded. And with SimScale, which is the world's first web and cloud-based simulation platform, we want to tackle these barriers and make simulation accessible to everyone. And yes, as I mentioned, SimScale is web and cloud-based. So what does it mean? First of all, you only need a standard web browser to access all functionalities of SimScale. You don't need to install any kind of software, update everything, install a license server, or something similar. On the other hand, it's also cloud-based, which means that all the computational power and all the storage is provided through the cloud. So you can use it actually from wherever you want. And the only thing you need, as I mentioned, is a standard laptop with a standard web browser and a working internet connection. Now let's try to, or now I would like to talk with you about some of the very special and unique things about SimScale. And the first things I would like to raise is that SimScale is actually the first real all-in-one tool. And what does it mean? Well, usually traditional simulation tools, you have to buy different modules with different licenses. Let's say if you want to do a CFD simulation, a fluid flow analysis, then you need the CFD module. If you now also want to calculate, for example, how these forces or how this pressure distribution will or which kind of stress will be created inside your part due to the aerodynamic loads, then you need to buy a structural model and so on and so on. At SimScale, this is the past because we have only one, let's say, one license type in the end of the day from a point of functionality, and every user can use the same features. And due to the cloud and web-based approach, SimScale is also super fast and easy. You can use it on any device. The only thing that you need, as I mentioned, is a working internet connection. And usually it's not only much faster than on-premise solutions, but also much easier to access your data since you can access it from everywhere in the world. SimScale also comes with a real-time support. And since our tool is a web application, it's a software service, we've gone new paths towards integration of the software and our support services. So you can access our support or contact our support directly through the SimScale application. As through our integrated chat, you can also use, if you want, phone and email. And beside support, we also offer consultancy, free webinars, and trainings. One thing I really love about SimScale, and here in this slide it's called cost efficient, but actually SimScale is free of cost because it comes with a very interesting and unique freemium price model, which means we have a free plan and professional plans. All the plans have actually the same kind of simulation features. The only big difference is that all simulations created with a free public plan are also available in our public simulation library, which can be used by other users as a good starting point or inspiration. And since we're talking about this, let's also talk a little bit about the collaboration functionalities. SimScale, first of all, has what we call the SimScale community. So it's really a network of 120,000 SimScale users and engineers. And you can discuss with them, ask them questions, get help from them. We also have several thousand public projects which you can import with one click to your own workbench and use as a template for your simulation. And besides this, SimScale is super secure. We have our own dedicated security team here in Munich, and these guys are really creating a very advanced security solution. For example, all the data is actually encrypted twice using government-approved AES encryption, and you have full control over your data as a professional user. Before we start to talk about the application of CFD for industrial blower design, let's also try to understand where CFD and simulation is used beside the, let's say, process engineering industry. So we have a lot of customers, first of all, from what is called the AEC industry, some from architecture, engineering, and construction. And there our tool, for example, our CFD capabilities are used not only to calculate like wind loads are acting around tall buildings or the wind comfort in a city, but also using CFD you can optimize, for example, components of the building technology like fans, ductwork, or you can even simulate the full ducting system and how it interacts with the environment and the rooms inside your building. And yes, besides that, SimScale is also used in a lot of other industries, including electronics, so where they use CFD and simulation like to find the best place for a heat sink or a fan, or to check if additional cooling is necessary. But as I mentioned, actually you can use simulation everywhere. So we even have customers from the field of healthcare and biomedical engineering, consumer goods, and for sure for valves, pumps, machinery, and process engineering. Well, now let's try to understand how we can apply CFD for industrial blower design and do our next step. in the case you have questions, don't be shy and just write them into the question toolbox. And as I mentioned, today we will talk about the optimization of industrial blowers using CFD. And first of all, what does I mean with industrial blowers? Because yeah, some of you maybe are not very familiar with the process industry. And in general, industrial blowers are used everywhere. And good examples are cement mills, the chemical industry, and wherever you actually where you have a need for mixing things, for example, or providing fresh air. And today we'll take a look at set up a case from a cement mill. And here the idea is that we have a kind of blower, which you can see here. And this blower is pumping the air inside this ducting system. And at the end of the ducts, we have different extractors and an extractor space. And usually, for example, what a scenario where this part of this is used is, for example, in a cement mill where you want to clean the cement dust. And there you actually, what you want to do is to have a very high and homogeneous mass flow or velocity distribution inside your extractor space. And yeah, here on the right side you can see some of the most important boundary conditions. So it's a compressible flow. It's also a turbulent flow, therefore we have to use what we call the turbulence model. I don't want to talk too much about theory, but maybe this is an important point and a point where a lot of confusion is happening. So turbulence is it's a phenomena which is not 100% understood until today. And since you will need a lot, you can see a nearly unlimited amount of computing power to solve turbulence, we use turbulence models, which simplify the effort of calculating the turbulent parameters. However, our setup is like we have an atmospheric inlet box here. So there we have ambient pressure of approximately 1 atmosphere. We have the blower, which is rotating with 261 radians per second. Yeah, and these outlets here are also outlets to the atmosphere. And what we therefore do is that we will use some smart boundary conditions, and that is the most important point whenever you do a simulation. First of all, think about what you want to do. So the outlet will work as a kind of, it will be open, and we will actually add the volume flow inlet here on this face. And yeah, now let's take a look how this works on SimScale. So the first step is what we call the CAD import. So first of all, you really need to prepare a CAD model and upload it. With preparing, I mean you need to make sure, first of all, that you extract the fluid domain, because in this case, we're not interested in the volume of the sheet metal which is used to build the part or the machine, but we're interested in the flow volume inside, which needs to be extracted first, and you also need to make sure it's watertight. The next step is what we call meshing. And meshing is about dividing your model into a lot of small sub-cells, sub-volumes, and later we are only calculating the physical quantities for the center of the cells, which means that the density of the cells is somehow our local accuracy of our simulation. And then the next step is to apply the boundary condition and to describe how our model is interacting with the environment. Then we can start simulation, and later, once the simulation is finished, we can visualize the results, understand what is happening, and do hopefully a good design decision. Now let's switch to the next tab. And what you guys can see here, it's the SimScale platform itself. So everything I'm doing here is happening in the web browser. And this is a project my colleague Darren prepared for me, so let's open it. And now you can see how you perform the different steps. And the SimScale user interface is dominated by this left bar. And this bar is like guiding you through all the steps of simulation. So first of all, we need to upload a design, CAD model. And yeah, you can like hide the different volumes or faces of the model, take a look inside and stuff like that. And once this is done, you can mesh your geometry. And by the way, as you can see, you can import a lot of different CAD formats, exchange formats like Sapis, IGES, as well as native CAD formats like SolidWorks or Rhino. Next step is to create a mesh. And yeah, therefore we will take a look at the base design again. This mesh was created fully automatic, so there was no need for any manual definition, which is necessary in a lot of other tools. And you just have to specify if it's an internal or external mesh and the overall fineness of the mesh. And here we go. This is our mesh. And as you can see, layer elements were automatically created. So to refine the velocity profile of the boundary layer. And after that, the final step is to set up the actual simulation. And there, yeah, you have to choose the mesh, the properties of the material, in our case air, and then we have the boundary condition. Here is the mass flow inlet. Here is the pressure outlet. And everything else is a wall. Yeah, and then you can create a new simulation run like this one, which was cancelled. Or for example, this one, which was finished successfully. And then you can, for example, take a look at different characteristic values like the mass flow through the boundaries, the temperature inside our system. You can also take a look at the development of other area integrals and area averages. And you can also take a look at the 3D simulation results. And this can take up to 1 minute because you should not forget that a bunch of data need to be processed and transferred at our systems. And yes, this is our simulation model. And the first thing I want to do is to create a cutting plane and visualize it with the velocity distribution. And now I just need to adapt. And then, I can like move the slice like this. Yes, and after this short demonstration, let's try to understand how we use CFD to optimize our system. And the main aim of this optimization is in the end of the day to increase the extraction performance of the system. And actually, we have two things we can optimize independently. First of all, the base system design, so the design of the ductwork and everything, like how everything is connected. And we can also optimize the design of the blower itself. And here you can see what we've actually changed. So first of all, we created a new version for this system where we used circular ducting work and also try to, use different lengths for the path to make sure we have a homogeneous pressure distribution. This is quite similar to what you do with the axis on a displacement engine. And regarding the blower, we used a smarter designed for the profile. So here you can see the initial blades were like just banded plates, while here we really have a kind of wing profile. And also we have a higher angle of attack and less curvature. And this allows us actually to test 6 different configurations. And now let's take a look at the simulation results. So take a look at the base design, it's the extraction ducts. It's obvious that we have a very homogeneous flow distribution. Guys, just to make it sure, can you still hear me? Is the audio quality still fine? Maybe some of you can write in the chat. Yeah, however, it seems to work. Yes, and oh, by the way, we got a first question by Sam, and Sam said that he was late for the webinar since he's from India, and he wanted to know if there's a recording of the webinar. And yes, we have a recording. We will prepare it and send it to you by email. All right. However, as I mentioned, a big problem here is that we have like a high flow velocity at the first outlet, and then it's like going down and down more downstreams. And this is not what we wanted to, because it will lead to a unhomogeneous flow distribution. So, and if we now take a look at the pressure distribution, some things will become more obvious. The reason why we have this high mass flux through the first hole and the low at the last hole is that we have a quite high pressure loss inside our duct, and as a result, the pressure difference between the extractor space and the duct is much smaller at the end, and therefore, as you can see, we have a lower mass flow through the outlet. And if we now improve the design, so we use this parallel ducts with different radiuses and a different curvature, we can see that it's much more homogeneous, and we actually have the same fluid velocity of around 5 meters per second at the outlet for all 6 or 5 outlet locations. And if we now take a look at the pressure distribution, we see the reason that the improved duct setup allows us an even pressure difference for each extractor. And since we have a nearly constant pressure on the extractor space, this result is a homogeneous distribution of the mass flow. And now if we can also visualize the flow rate through the different extractors and try to quantify our observation. And here you can see it like that with the initial design, like it's a linear loss of flow rate over the extractor number, while with the improved design, which is yellow in this chart, it's more or less homogeneous and constant. And another big problem is that you have with the base design, or found out about the base design, is that we have flow separation with circulation inside the elbow. And the reason is that the high local velocities which we have in this area lead to low pressure regions, the law of Bernoulli, as you know. And therefore, this increases the viscous pressure loss. And at some point, this pressure gradient is too high, the flow can't follow anymore, and then it will deattach. And if we compare it, it seems like and take a look at the pressure values, it becomes more obvious. At this point, the flow is not able anymore to follow the pressure gradient, and therefore it separates. If we now take a look at the improved design, we try to reduce the high velocities and the overall flow velocities by having a higher diameter and to smooth the transitions. And it shows that we still have a small separation. However, the separation and the blast inside, so this blue area, is smaller, and therefore we have less losses. And in numbers, it means that we were able to minimize the pressure difference by 50% from 200 Pascal to around 100 Pascal. And now let's take a look at the blower design. And on the first slide, you can see the velocity distribution for the initial design. And it's obvious that we actually have flow separations on all of the blower fins. And one reason is that the angle of attack is obviously so high, but also the profile we used is not optimal. And now if you take a look at the improved blower, we still have this kind of separations, but they're much smaller. It seems also that the large separation on the upper surface was fully removed. And we could even do a further improvement by reducing the trailing edge flow separation by increasing this curvature here. Now let's take a look at some nice visualizations we created. So these are the streamlines through the blower at 2,500 rotations per minute. And this is another great feature about CFD. It really helps you to understand what is happening, and as a side effect, it creates some nice images which you can also use for your presentations, when you present, for example, your design proposal to customers and so on. And we also prepared a video where you can see like how the velocity field or how the velocity streak lines are moving relative to the blower fins. Maybe once again. All right. Now I would like to take a look at some of the, I would like to summarize the results we discussed. And first of all, we created this simple chart, which is giving you the flow rate, or the volumetric flow rate against the RPM for all three different designs. And here you can see like that how much we were able to prepare or to improve the performance of the base design. And actually, the improving the ducting system had a little bit, but the big difference was made by the improved blower itself. And if we summarize this, overall, my colleague needed around 3 hours of manual time to prepare the CAD model, export this, and run the simulations. For running the simulations, we needed 24 hours of computing time. So the whole power turnaround time was a little bit more than 27 hours, so overnight, you can say. And in total, they used 1,500 core hours for all 6 configurations. And in return, we were able to improve the extractions. We were also able, we could also show and find out where we can do further improvement. And compared to physical testing, we saved a lot of time. Thank you very much, yes, for your time so far. And now we have our Q&A. So in the case you have questions, just write them into the question box, and I will try to answer them. All right. It seems that most of the questions were answered during the session by me on the chat. So if there are no further questions, yes. Okay. It seems like there are no further questions. So in the case later there is something you would like to discuss with me, you can also reach out to me by email, mmurphy@simscale.com, Thank you very much for being here with us. It was a big pleasure, and we will send you the recording of this webinar session at Friday by email. Have a nice day. Bye.